one team, one vision, one goal. An interplanetary travel to look for extraterrestrial life in the nearest galaxy. A flyby mission of a planet outside of our solar system, starting and ending within a human's lifetime. This is Explore. We are NUE, consisting of 16 international multidisciplinary students representing 9 countries, enrolled in the master's degree of the International Space University, ISU, in Strasbourg, France. Our mission is called Explore, which stands for Exolar Proof Laser Propelled at Relativistic Speed. Our goal is to use direct energy to accelerate thousands of small proofs to 20% the speed of light. Within only a few decades, they will reach Proxima b, an exoplanet orbiting the closest star to our Sun, Proxima Centauri. Welcome again! We are here today to talk about the engineering aspects of Explore mission. For that, I warmly welcome Aashish Sarode and Kyunghwan Kim, professionals in the engineering aspects of this mission. Welcome.
Thanks for having us.
Thanks for having us.
Can you explain us a little bit about your background, your professional background, please?
So, I'm an architect in France, and also I'm a space architect.
As for me, I have an engineering background. I am more specialized in aerospace engineering, and that's it.
Okay, thank you so much. So we will take a closer look into the parts of the hardware of the mission, the materials, another interesting point in the engineering phase of this mission. I'm gonna ask you a question. To achieve the goal of reaching the Alpha Centauri system within approximately 28 years, system design is critical. Therefore, the first question is how this mission works from an engineering aspect. So, who wants to answer me? Okay,
I will
Aashish,
answer that question.
go on.
First of all, this mission is very complex in itself. So for our simplicity, we have divided this mission into 2 parts. First is the ground segment, and the other one is the space segment.
Oh yes, we will have the next guest we have is Julia Knie, who is gonna talk about the ground segment of this mission.
Yeah. So in the space segment, there are more 2 subsections. The one section is the satellite section, and the other section is the probe sections. In the broader term, we call it as a probe for our simplicity. So in the whole engineering design is very complex for these systems too. But to make it very simple, the mission sequence will be like, first we are going to design a mothership, which is a satellite segment.
Okay.
In that we are going to carry at least 5,000 probes to the geosynchronized Earth orbit, where it is going to stay. Its lifetime will be around 10 years, so that it is going to be stay on the same position at the same time for 10 years, so that we didn't go offset and we don't have to adjust the lasers every time. So
interesting.
So in that, the probe is going to be inside in the mothership, and every day, every night, basically to be specific, every night we are launching 4 probes of different payloads every time. And to do that, the mothership will have a robotic arm which is going to be precise enough, which is going to be calculating the attitude determinations, attitude corrections of every single launch of it, and it is going to be pointed to the Proxima Centauri after 20 years. So basically the Proxima Centauri now we are seeing is 4 years back. So we know that the distance between Earth and the Proxima Centauri is 4 light years approximately.
Wow, that's That's far away.
Yeah, that is. So when we see from our telescope the Proxima Centauri, so we see the position of that Proxima Centauri 4 years before. So we have to take 4 years plus 20 years because the probe will go with 20% the speed of light.
Wow.
So at that point we came to the calculation that it will take around 24 years to reach our probe to the destination, where to do the flyby mission over Proxima B, to be precise. And after that we thought that it is going to be way more complex. So this mission has been done. This mission is basically on the broader scale, has been defined by Breakthrough Starshot. Our whole mission is inspired by them, but the main difference between our team and the Breakthrough Starshot is very much focused on the probes, but our designing team is more focused on the mothership, that how we are going to launch from Earth to the Proxima Centauri.
Okay, that's super interesting.
Yeah.
So we can say that it's a long-term mission, right? Because
Yes,
wow.
it's a very long-term mission. It can be a multi-generational mission, because the first 20 to 22 years is just the probe is going from Earth to the Proxima Centauri.
It's only traveling.
It's only one way. But when it will try to communicate, the communication link will take at least 4 years to reach to us.
Wow, there is a huge delay in the communications.
Yeah.
Like with Mars. With Mars, we have like 7 minutes of delay for the communications return, and with Alpha Centauri, it's 4 years.
It's 4 years.
We can do that huge comparison.
Yeah.
Like we can see how far away it is.
Yeah, and we will only get that the spacecraft has been reached to its destination. Only that, and then it will take that if we want to make some corrections or attitude corrections or something, that codes will be sent to the spacecraft, and it will take 4 years again.
Wow.
So 4 years there, but the attitude is currently on the real time at that time at that location. So the codes which the spacecraft will reach is 4 years back. So there is a 4 years delay, and Breakthrough is also trying to look into it, that how the communication can be established in the faster way, so that we don't have to deal with this. So more techniques are coming out, like gravitational lensing, relay satellites, or some more research has been going on, and I think in the coming future it can be solved at some point.
Okay.
So I'm looking forward to that research.
That's amazing. That's super interesting.
Mm-hmm.
Okay, so thank you so much, Aashish, for this approach for the mission, and let's continue.
Thank you.
I have another question. So we talk a little bit about the ground segment and the space segment, but let's go a little bit deep into the space segment. So Kim, what is the main hardware for this mission? What is necessary for our goal? Can you tell a little bit?
Yeah. So the space segment is composed by two sections, mothership and probe.
Oh.
So the mothership is going to be transported by a launch vehicle from Rocket Lab in New Zealand. It's going to be launched in 2036, and the rocket vehicle is a Neutron. So the mothership has 5,000 probes inside. So since propelling spacecraft by laser energy is extremely complex for this mission, so that 10,000 chipset probes would be sent to Alpha Centauri for increasing the probability of this mission. So four different types of payloads to taking pictures, homochirality, and biosignature detections are going to be installed in each probes. The dry mass of mothership is 1,000 kilogram, and the height of the mothership is 5.5 meter without deployed robot arm, and it has 6 years of life cycle, but it can be extendable up to 15 years to recycle it later. There is about 5,000 probes inside of the mothership, and it's going to be resupply in 2038 by second launch. By second launch.
So in 36 the launch, and in the second launch,
2 years later,
it will be deployed.
Yeah.
Okay.
So there's a 2 launch in total. In future, we can expect about the reusability of this mothership, thanks to the fact of that size of satellites is getting smaller, right? And orbiter deployer deployer market of satellite is growing recently, such as D-Orbit company.
Okay.
So they send a platform in orbit, and they deploying multiple satellite at the same time to increase the money.
That's interesting.
To increase to reduce the cost.
Okay.
So we can use our mothership as a platform to send other types of chipset into our solar system, or some chipset satellite for other observation.
Super interesting. So we already talked about the mothership, and now we are a little bit curious about the proofs and its materials. Can you talk a little bit about that, Kim? Thank you.
Of course, yeah. So the probe mass is about it's really light. It's about 10 grams, and if it's when it fully deployed, the sail size is about 7.5 meter of scale.
Wow.
When it folded, it's like 20 centimeter. It's really small. And the chipset is much smaller than, it's like 5 centimeter of chipset is center of the sail. So this origamic sailing system is going to be deployed by robot arms. So the robot arm on the mothership is going to pick one probe and then orient it to the trajectory to the Alpha Centauri, and then the end grabber of the robotic arm is going to be rotated to deploying the sail.
Oh, interesting. Like a space dock. Like it takes it and it put.
Yes.
Okay.
And then, so the material is really important here, because we have solar sail and light sail prototype already launched in orbit by JAXA and Planetary Society.
Oh yes, I heard about it.
Yes.
So interesting.
It's a very successful mission, but they use solar energy as an energy source. But our project use laser as a energy source, which is really, really powerful, and it is really hard to find the correct material which has high tensile strength and with the dimensional and chemical stability against this high laser power.
I can imagine. So thank you so much, Kim, for this approach for the mothership and the proofs. But could you talk a little bit more about materials?
Yes. So our probes has graphene sail.
Oh, I heard graphene is super good. Super good material for space missions, right?
It's quite futuristic material right now, because it's still R&D level.
Mm-hmm.
So solar sail used polyamide resin kind of material, and the light sail used a kind of polyester film, sort of polyester film material, but ours cannot use those material because laser going to be damage those kind of material sail. So right now graphene, like we said, is the most possible material for us, but again we need more research on it to make a huge size of sail. It's not possible. We don't have technology on that. Mm-hmm. But
because we need a huge sail.
Yes.
And a super light sail, right?
Yeah.
To go fast as it's gonna be,
yes.
Because it's gonna be a 20% of the speed of light, right?
And graphene is really light, so it's perfect material. But right now it's really like first step to go to how to make it bigger and test with lasers. And
Okay.
and already ESA had a already interesting experiment in the drop tower in Europe. We had a drop tower
Oh yes.
to test the gravity.
The European Space Agency.
Yeah, and European Space Agency made a like 3 millimeter of graphene sheet,
Okay.
and then tested with the laser of 1 watt.
Oh.
It's really small, but they proved that it works actually. It was really weak power, but it was interesting to see that how it, not just theoretically, but in reality, it works. So currently, the biggest challenge for this material is money, because this is the most feasible material. It's very thin, and also it's really hard to fold the sail multiple times. It's really hard.
Okay.
But graphene but the printed graphene sheet is going to be possible. The only problem here is to print it in bigger size. So this is the biggest challenge. But recently, ESA funded some startup to collaborate together to grow up the graphene market. So
Okay.
that's the good thing we can expect the further research or development of this technology.
Wow, that the European Space Agency is investing on this
Yes.
material is very important and impressive.
Interesting. Yeah.
Okay. Thank you so much, Kim
Alright.
and Aashish.
Thank
So let's continue with the next question. Are the laser sail mission news? Like, as I understood, there are some kind of missions going on, right? Like with JAXA and with Planetary Society. They already did, I think, 3 missions or something like that. Can you explain us a little bit about it?
Yeah, thanks for
Thank you.
asking. So, like you said, JAXA tested Icarus solar sail, and the size of the solar sail is impressive. It's like 14 meters of scale.
Wow,
it's
that's a lot.
huge. It's bigger than ours. But the mission wasn't very successful because of the complexity of deployment system. The planetary science team's solar sail called light sail was much smaller than ours. It's like 5.6 meter of scale.
Okay.
It's smaller, but it was the most successful mission of solar sail. So those sails are such a good references for us because we can understand how we can fold the sails and how we can deploy the sail, because it's really complex.
Yeah, we need to do a lot of proofs on Earth before going into space, right?
Yes,
It's
yes.
super
It
important
must
in
be
the space
smooth
industry.
deployment in
Yeah.
the Soviet in
And a lot
space.
of money is gonna
A lot
be
of money,
invested.
yes.
So yeah.
So normally they use a boom structure. It's called boom structure. It's like really light structure. They like ruler, in the construction site. They just deploying it and dragging it the sail
Oh.
all sides.
Okay.
But it's quite heavy for us. So we use the boom wire structure, like really thin wire is going to be deployed by rotating mechanism. So yeah, I cannot say this is a new system,
Okay.
but we learned a lot from solar sails and light sail. But also there is a already laser sail from BTS team, so Breakthrough Starshot team. So we learned a lot from them too.
Oh yes. Okay, that's very interesting. Thank you so much, Kim.
No worries.
So very interesting our conversation, and I have one last question for you. So, what are the most challenging parts of the projects from the engineering perspective? Can you tell me a little bit about this?
Okay.
Because they should be a lot, right?
Yeah. The first challenge which we got from the mission when we got the topic is how we are going to design this whole mission in the first place. Like, the complexity level of this is very extreme, and most of the technology which we are currently working on is,
So we don't have the technology yet. To do
the
it.
technology.
Wow.
As per NASA's technology readiness level, most of the technologies are around 2 to 3. So basically, it's very low, and it is under R&D works. So
Okay.
to make this thing happen, we have to assume lots of things, like how the mass of the probes, the length of the probes, and most of the data which is not on internet is not viable, and which is not proven or which is not peer reviewed yet, and the materials which we are going to use, like most like the one conference which was from Breakthrough Starshot, which was held in Caltech.
Yes.
They have some interesting research going on materials. They are using some nanostructures to make the sails more lighter and more feasible. But till now those are on the nano scale, which is not possible to make a 7 or 8 meter long sheets or something.
Yeah, that's true.
Yeah, so it's very so I've personally I found that the materials is not in the current readiness level, so that is one drawback for us. That is the biggest challenge. And the second one is the communication in fields. Like there are 3 types of communication which personally I think that which can be feasible in this mission. The first is the optical communication, the second one is the radio communication, and the third one is the quantum communication, which is in the very early stages in its development.
Oh, I know that communication in space is always a problem.
It's always a problem.
And could you explain us a little bit what is, radio communication, optical communication, and quantum communication?
Yeah.
Only to have a little idea about it.
Yeah, sure.
Thank you.
So the first one is the optical communication, which I'm going to talk. So optical communication is basically the communication between 2 points through light.
Okay.
So if there is no light, then there is no communication between 2 points.
No light, no communications.
Yes.
Between 2 points.
Yes.
Okay.
The next one is the radio communication, which we use the radio frequency, like mobile phones, Wi-Fi connections,
The spectrum,
etc.
like.
Yeah, the spectrums.
Okay.
So which are mostly in the infrareds, which we can't see by our naked eyes. So
Okay.
Those type of communications, most of the ITU, the International Telecommunication Union, they have the hold on those type of spectrums. They specifically ITU decides that which spectrum will be allotted to which country and which sector.
Yeah, because the International Telecommunications Union is in charge of.
Is in charge of those things.
Yeah. Of the spectrum and orbits, right?
Yeah, and if we go with the radio communication, the first question our mentor asked is, we are launching 10,000 probes, and are you going to give each probe a separate frequency band? That will be very difficult.
Wow.
So
difficult.
yeah, so as our engineering team come up with a solution that if we are launching 4 probes per night, so each probe will have different band frequency in
Okay.
it, so that they don't interfere with their communication systems.
Yeah, because interference between each other
is very bad. It's very bad in the space
it's
communication.
a super risk.
Yeah.
Yeah.
So we have decided if we are going with the radio communication, because radio communication is the only way which is very feasible in our current state. We don't have much R&D in optical communication as well as in the quantum communication. So radio communication, we use 4 frequencies for 4 probes each day, every day.
Okay.
So the one thing which is solved, that we don't have to take 10,000 frequencies from ITU. We only need 5 bands, 4 for probes and 1 for mothership, obviously. So the last one is the quantum communication, which I think that quantum communication is in the vague way, it's very difficult to understand, but if we put in the simple form, example, there is a point A and point B at the 2 surfaces on the earth, and there is a satellite which has a quantum communication capability to communicate. So what the satellite will do is, it will take 2 photons. Photon is basically a single unit of light in the waves, in the particles waves.
Okay.
So both 2 photons will be interconnected by which is known as quantum entanglement. So 1 photon will be sent to the point A, and 1 photon will be sent to the point B by the satellite for the initial establishment of connections. And what you do, that there is an electron spin happens in the photons, more molecular. That's very deep, so I will not go there. But once you flip the photon from from position upsideward to the downwards, at the point B, the photon which is interlinked will do the same thing. So at that point, we as a physicist thinks that if you flip the photons, or if you flip the electron spins, if you count the electron spins, the same happens on the second photon, which is quantum entangled with each other. So that's the fastest way to communicate with anything in the universe.
So the quantum communications is the ideal one.
Is the ideal.
But it's impossible nowadays.
It's impossible for current generation, but maybe it is possible for next 20 generations, because China is developing its first quantum communication, and it is pretty much very successful.
With quantum communication, we could fix a lot of problems into space.
Yes.
There are researches ongoing in Europe too. So
yeah.
That's amazing. So thank you, Aashish, for this approach. What I understood is that there are three kind of communications, right? So there is the radio communications, the quantum communications, and the optical communications. And the radio one is the most feasible right now, right?
Yes.
Because the quantum communications are pretty impossible right now, and we should wait a little bit. We are developing also in China and in more countries, but specifically in China. And the optical communications, what I know is that is being developed and is going to be super useful into space. But it's true that we have a huge problem, because I know that ITU doesn't have into their plans to regulate these laser communications, right?
Yeah.
So we will have a huge risk with the encrypt messages, and I know actually that China sent an encrypt message through optical communication into the ISS, and it was impossible to decipher for NASA and the other space agencies involved in the ISS. So it's pretty interesting, this part of the mission. The communications is a huge challenge.
Yeah, like in communication we can think like that, like radio communication is the least hack proof. The optical is more stronger hack proof, and the quantum communication is next to impossible to hack any communication between 2 points.
So as we say, the quantum communications is the ideal one.
It's the ideal one. It's very ideal.
Okay. So thank you so much, Aashish, for this knowledge that you bring to this podcast. And due to the considerable risk of failure, the prospect of sending out thousands of probes will increase the probability of achieving the mission. And I want to say thank you very much for our amazing guests. Thank you for being with me today, and for the entire knowledge that you bring to this podcast.
Thanks for having us to this podcast.
Thanks for having us. It was very, very interesting talk, and we are pleased to share our missions and project with you.
Thank you so much.
Thank you.